Hello everyone, today I will present my final project. In this presentation, I will focus on how I improving the dice score in angiography segmentation and what I learned from these experiments. This presentation is organized into 4 parts. First, I will briefly summarize the motivation and problems identified in previous proposal. And second, I will introduce my main approach and experiment design. Third, I will analyze the experiment's results in detail. And finally, I will conclude with key findings and future work. Angiography or CAG is widely used to diagnose artery disease. Accurate vessel segmentation is a critical step for downstream tests, such as stenosis estimation and syntax score calculation. However, this test is challenging due to low image contrast, strong noise, and thin vessels, and most importantly, inconsistent ground truth annotation. My goal is to build a stable and topology preserving segmentation model while minimizing the cost of manual annotation. There are 3 major problems to these tests. And first, baseline UNet or other existing models often produce fragmented vessels and fail to capture thin distal branches. Second, the dataset itself may have some limitations. Its ground truth labels may be imperfect and expensive to obtain. This motivates the use of pseudo labels. And third, commonly used laws such as dice or cross entropy focus on pixel overlap and do not enforce vessel topology consistency. And these problems makes vessel continuity particularly hard to learn. Before introducing my method, I would like to briefly explain how my work relates to existing approaches and what makes it different. First is most existing vessel segmentation methods rely heavily on clean and consistent ground truth annotation. When the annotations are reliable, these models can achieve strong dice scores. And second is topology-aware laws like CL dice were proposed to preserve vessel connectivity, especially for thin structures. However, CL dice assumes that the ground truth skeleton itself is stable and accurate, which is not always true in the arcade dataset I used. And last is pseudo leveling is another common strategy to reduce annotation cost by expanding the dataset. But pseudo labels may inherit the model's own bias. So instead of proposing a new architecture, my work focuses on understanding why dice score is difficult to improve under noisy supervision. And I will compare pseudo leveling, CL dice, and test time augmentation under real world annotation noise in the following experiment. The key difference of my work is that I show the main bottleneck is not the model itself, but the limitation of the metric and the annotation quality. Based on the limitations of existing methods, the key question becomes how can we meaningfully improve dice score under imperfect supervision? In angiography, the main difficulty is not model capacity, but the fact that ground truth masks are noisy and inconsistent. Therefore, instead of fully trusting the single supervision source, my idea is to introduce multiple complementary constraints during training and inference. Especially, I explore three directions: expanding supervision using pseudo labels, and then enforcing structural consistency using topology aware loss. And last is to improve robustness and add inference time using test time augmentation. These ideas directly lead to the following experiments. As for model architecture, my backbone is MI-UNet, which is based on the UNet architecture. It uses depth-wise separable convolutions and a gated mixing block inspired by Mamba. However, it does not use Mamba SSM or selective scaling. This design is lightweighted, stable during training, and compatible with pseudo-labeling and topology-aware losses. Why not use full Mamba is because full Mamba relies on sequence-based selective scaling operations, and it's difficult to apply to 2D image segmentation. And also training will be unstable, and GPU memory usage is high, and retrain cost is significant. And thus, a Mamba-inspired convolutional design is a more practical choice for CAG segmentation in my project scope. And the following are the experiments I try to improve dice scores. And first is pseudo-label learning. The purpose of this experiment is to expand the dataset without manual annotation. I generate pseudo-masks using a previously trained model and mix ground truth and pseudo-labels during training. I do not apply pseudo filtering, and all pseudo labels are included. This helps improve generalization and mitigate annotation noise. And in experiment B, I introduce CL dice loss, and it preserves vessel skeletons and encourages continuous center lines, especially for thin branches. It combined with dice and or cross entropy loss in this experiment, and is designed to reduce vessel breakage. And experiment AB combines the previous two experiments using the expected benefit is better vessel continuity and generalization. The final experiment is further applies small angle test time augmentation and horizontal flipping to improve robustness. This is the experimental settings I use while training. And this is performance summary. And overall, the baseline model is already strong and stable across faults. Pseudo leveling provides small dice improvement, and CL dice alone leads to a significant performance drop. and combining methods partially recovers performance but does not exceed pseudo-labeling alone. And last, taste time augmentation contributes very little. And next, I will try to analyze the results. Pseudo labels help by increasing the effective training set size and exposing the model to diverse vessel shapes. They provide small but consistent dice improvement. However, the improvements are limited because pseudo label quality depends on the model itself. And although CL Dice is designed to preserve topology, it performs poorly in arcade, and skeleton extract is unstable, and ground truth topology is inconsistent. As a result, CL Dice amplifies annotation noise and causes dice to collapse. This shows that CL Dice requires a more cleaner topology ground truth, which arcade dataset may not provide. Combining pseudo levels and CL Dice stabilize training slightly, but does not surpass pseudo labeling alone. Test time augmentation improves precision marginally but often reduce recall, leading to negligible net gain. Overall, combined approaches do not meaningfully improve dice under arcade conditions. And why dice doesn't improve as expected? And I think the reason is that dice is extremely sensitive to small pixel level differences in thin vessels, and arcade annotations vary in thickness and continuity, causing unfair penalties. And also, topology correct predictions can still receive low dice scores, and therefore dice does not fully reflect visual or clinical correctness in this dataset. So, my key findings are dice score is limited by annotation inconsistency, and CL dice is unreliable when topology ground truth is noisy. And third is data strategies outperform loss-centric ones. And last is major improvements likely require stronger architectures or better annotations. In conclusion, MI-UNet baseline is difficult to surpass, and pseudo-labeling offers mild improvement. CL dice is counterproductive in this dataset, and taste time augmentation provides negligible benefit. None of the attempted techniques significantly improve dice beyond the baseline due to dataset and metric limitations. So I think the future work is to do more label refinement and multi-task learning with center line prediction, and find more topology guided augmentation methods, or find some higher capacity models like Mamba based backbones. And last is to confidence based pseudo label learning. In this project, I was inspired by these previous studies, and detailed citations are listed on this slide. Thanks for listening.